discussed the tenets of electrostatics, learned a little bit about electric fields, potentials, some computations related to the same, and related stuff. Now, a previous session was dedicated to conductors, and we hopefully got comfortable with the basics related to conductors and the ideas and the ideologies involved. Now, extension of conductors, but essentially an application. So if I have a spherical conductor, say, of radius r, and I assign charge q to this conductor, then the potential of this conductor gets raised to, kq by r. Yes or no? Isn't it? Now, very clearly, if I double q, v gets double. K and r are constants. K is 1 by 4 pi epsilon naught. R is the radius of the conductor. If q is doubled, v is doubled. If q is halved, v is halved. Yes or no? Essentially then, the ratio q by v, which is r by k, which is 4 pi epsilon naught r, this ratio q is to v remains constant and is equal to 4 pi epsilon naught r. Yes or no? If charge is double, v gets double. If charge is triple, v gets triple, but the ratio charge to increase in potential remains constant, right? And this constant depends on what? Number one, the medium. Epsilon naught is about the medium. It would have been, if it would have been some other medium, it would have been epsilon naught into the dielectric constant of the medium, right? So the medium factor comes into the picture and the geometry factor comes into the picture. This ratio does not depend on charge or v. It depends on medium and the geometry. So this ratio for any conductor depends on, number one, the geometry of the medium, geometry of the conductor, beg your pardon. Number two, the medium, geometry of the conductor and the medium in which the conductor is placed. Yes or no, right? Now, essentially, there is potential energy associated with it. Just outside the conductor, there is an electric field generated by this conductor. Yes or no? And greater the value of q, the greater would be the value of v, and the greater would be the electric field produced in the surroundings. Right? And it's not like you can keep assigning q and expect things to be right all the way. As you keep assigning more and more charge q, the electric field just outside the conductor, which is most vulnerable, goes on increasing. As you move further away from the conductor, the electric field falls as 1 by r squared. But just outside the conductor, the electric field is the maximum it could be. And goes on increasing as more and more charges assigned to the conductor. So this region is a vulnerable region and is susceptible to what is referred to as a dielectric breakdown or an electrical puncture of the medium. If there is a certain value of q, then that might raise the electric field just outside the conductor to such a value that the medium is not able to withstand that value of the electric field, and the medium is no longer non-conducting, it could become conducting. Yes or no? And the charge that accumulates on the conductor could get lost into the surroundings. Could get lost into the surroundings, right? So, for sure, one thing, that there is an electric field produced in the surroundings, right? There is energy associated with that electric field. There is energy associated with that electric field, and that will depend on the charge q that I have assigned, right? There is that the energy associated with the electric field in the surroundings is referred to as the potential energy, sometimes also referred to as the strain energy. It's prevalent all in the surroundings, you know, from the conductor to outside the conductor up to infinity. That energy is prevalent, and that's the potential energy of the system. It's also called the strain energy. It's also called the strain energy. It's a very deep-rooted issue to very readily say the energy lies in the surroundings, but for convenience we'll say, okay, the energy lies in the electric field in the surroundings, it extends up to infinity. Now that's energy is also called strain energy, the potential energy, and you could realize that energy. For example, you know, you could connect this conductor to another uncharged conductor, and there would be flow of charge, there would be current generated, there would be heat generated called Joule heating, right? So it's that potential energy, that strain energy, which could get realized as an electric current, as Joule heating, and so on and so forth, right? So for sure, if a charge q is given to this isolated conductor, there is energy associated with the conductor. Strain energy, also referred to as the potential energy of the conductor, and it could be realized. Depending on how we want to realize it, we could realize this energy, right? So this then is a very crude way of storing electrical energy. This is a very crude way of storing electrical energy. Yes or no, right? Assigning charge to a conductor, raising its potential to a certain amount, by means of which I save energy in the surrounding medium. There is strain energy associated, which could get converted into other realizable forms of energy, right? It's then a mechanism, a very simple, naive mechanism to store electrical energy. Store electrical energy, right? When we talk of electrical energy being stored in the surroundings, then we refer to that as strain energy also. We refer to that as strain energy as well, right? Now, in a very general sense, in a more general sense, the conductor could be of any shape, right? Need not be spherical, it could be of any shape. For example, the conductor could be of an arbitrary shape, and if I assign charge q to this conductor, its potential gets raised to an amount v, and on doubling the charge q for the same geometry and the same medium, the potential will get doubled. On tripling the charge q, the potential v will get tripled, and so on and so forth. Essentially then, for any arbitrary shape, the fundamentals don't change. The charge assigned, which causes the potential v to which the conductor gets raised, remains a constant for any conductor, This constant will depend on two things. Number one, the geometry of the conductor, and number two, the medium of the conductor. Yes or no? The amount of charge q and the potential v to which the conductor gets raised subsequent to having assigned a charge q. And this then is a property of the conductor. Not the amount of charge q that you give to the conductor. It depends on the property of the conductor, right? And this property is referred to as C, the capacitance of the conductor. This is referred to as the capacitance of the conductor. coulombs per volt. Coulombs per volt. It's a, like I said, it's a means of storage of electrical energy. It's a means of storage of electrical energy, right? And coulombs per volt. This has SI units called farads. Farads. F-A-R-A-D-S. A farad is a very large unit of capacitance. A very large unit of capacitance. In fact, a conductor of the size of Earth would have capacitance of the order of farads. Right? So, farad is not a practical unit of capacitance. A more practical unit of capacitance is a microfarad or a picofarad. A micro is like 10 to power minus 6. A pico is like minus 12. And a nanofarad, which is minus 9. Nanofarad is 10 to power minus 9 farads and so on and so forth, right? So, mostly we will use microfarads, which is like 10 to power minus 6 farads. So, conductors of the order that we use in real life have capacitance of the order of a few microfarads, which is like 10 to power minus 6 farads. Got me? Now, what we now modify into is a different kind of an arrangement where, suppose this is a conductor. On assigning a charge Q, the potential to which the conductor gets raised is V if it's an isolated conductor. And the capacitance is Q by V, right? Now, very clearly, for the same charge Q, if a conductor gets raised to a lower V, then it produces smaller values of the electric field outside, and therefore it can withstand more amount of Q. It can withstand more amount of Q before a breakdown of the surroundings occur. Therefore, if a conductor gets raised to a lower potential for the same amount of charge Q, then it has a higher value of capacitance. It can act as a better means of storage of charge. Yes or no? The limitation to the charge you can give to the conductor depends on the dielectric break property of the surrounding medium. Yes or no? Now, instead of an isolated conductor, let me think of a pair of conductors, right? So this was an isolated conductor originally, and it got raised to a potential V when a charge Q was assigned to it, right? Now what I do is, in the proximity of this conductor, let me bring another conductor. In the proximity of this conductor, let me bring in another conductor. And if plus Q has got assigned to this conductor, then on the nearer surface of this conductor, a negative charge would get induced, right? And on the further surface, it would be residual positive charge maintaining electrical neutrality of the conductor. Yes or no? So now we have a pair of conductors. Now we have a pair of conductors. Now, what would happen in the process? What would happen in the process? In the process, realize that this negative charge would lower the potential of V, of this conductor. So V will get reduced because of this. Because of these positive charges on the farther surface, the potential V will get increased, right? So there are two opposing effects because of this conductor in the proximity. This negative charge results in lowering of the potential, whereas this positive charge results in increasing of the potential V of this conductor. Yes or no? You know what I'm saying? But this being closer compared to this has a more pronounced effect compared to this. This being closer to the conductor would reduce the potential more than the amount by which this increases the potential of this conductor. Yes or no? You know what I'm saying? Therefore, very easy to say and suggest that the net effect of this conductor is to lower the potential of this conductor. Yes or no? This has reduced the potential, this has increased the potential. But the reduction caused by this in magnitude is more than the increase caused by this. Therefore, the net effect is lowering of the potential V of this conductor. Yes or no? Right? Therefore, if V gets reduced, Q by V will get increased. If V gets reduced, Q by V will get increased, and therefore the capacitance increases. The capacitance of this pair is more than the capacitance of an isolated conductor. Capacitance of a pair of conductors, therefore, is superior compared to the capacitance of an isolated conductor. What do you think? Right? Got me? Clear? Makes sense, right? Now, suppose I earth this conductor. Suppose I earth this conductor. See, essentially, these negative charges were electrostatically bound to these positive charges, right? So these were charges, these were bound charges, and these were free charges. These charges were given stepmotherly treatment. They were repelled, right, and thrown out. And that is where Mother Earth behaves like a real mother. It says, all right, if you have nowhere to go, you can come unto me. So these charges then are assimilated by the very benevolent Mother Earth, and they flow on to the earth. Flow on to the earth. This is what happens. This is what Mother Earth does always. If it finds an unattended charge without a parent, without a guardian, it says, all right, all into me. There these charges flow, and the positive charges conveniently are assimilated by Mother Earth. Now, you're simply left with these negative charges. So the increment caused by this is taken out, and therefore there is a further reduction in potential. There is a further reduction in potential because the increase caused by this has now vanished because there are no more of these free positive charges available, and therefore V further decreases and capacitance further increases. This is what transpires. Yes or no? Right? All's good? Now the potential difference between these two becomes V, because this is at zero potential. The moment you connect something to Earth, it acquires the potential of Earth, and Earth is a reference of potential. It is zero potential. It is zero potential. Earthing essentially is reducing an entity to zero V, zero potential. That is earthing principally, right? So Q by V then has a higher value compared to what it was with an isolated conductor. So a pair of conductors will offer a better and a more efficient mechanism towards storage of electrical energy. It's capable of storing greater Q and yet not cause the surrounding medium to break down electrically. Fair enough, right? Now, suppose I have a pair of plates like we discussed, two very large plates, conducting plates separated by a small distance d. Two very large conducting plates separated by a small distance d. D, like I said, is small compared to the square root of area of overlap of the two infinite conducting plates. Right? Recall all of that? Now, if a charge Q1 is given to this and a charge Q2 is assigned to this, charge q1 given to this and charge q2 assigned to this, then these charges will get delegated on the 4 surfaces. These two are the inner surfaces and these two are the outer surfaces. The 2 outer surfaces then become party to q1 plus q2 by 2. Right? The 2 inner surfaces acquire q1 minus q2 by 2, q2 minus q1 by 2. Yes or no? Recall this? And the field in the meet of both the conductors would be 0. Field in the meet of both the conductors would be 0. Now, in between the two conductors then, say this was q, this was minus q, isn't it? If this is small q, this is going to be minus q, right? And the 2 outer surfaces are q1 plus q2 by 2, right? Same charge on the 2 outer surfaces, right? Let me call it q outer here and q outer there. Q outer is q1 plus q2 by 2, as we've seen earlier, right? Now, in between the 2 plates, there is a uniform electric field produced. Uniform because D is small, so for this region E could be looked upon as practically uniform. D is very, very small, right? And if I look at any point P here, then the field because of this Q naught and this Q naught would be in opposite directions and would cancel off. Right, this is Q naught on a very large plate, so Q naught by 2A epsilon naught is the field it produces at P to the right. Q naught by 2A epsilon naught is the field produced at P to the because of this. So the outer surfaces are not, the charge on the 2 outer surfaces are not participating in producing an electric field in this region, yes or no? They're not participating in producing, so then who's producing electric field at P? At P. The field produced by this plus Q is Q by 2A epsilon naught to the right, Q by 2A epsilon naught to the right. This is like an infinite sheet of charge Q spread over an area A, right? So Q by 2A epsilon naught A is the field produced by an infinite sheet of charge, right? And this minus Q naught would produce a field at P which is minus Q by 2A epsilon naught to the left. Yes or no? The net at phi, so minus q by 2a epsilon naught a to the left is like q by 2a epsilon naught to the right. So the net field at P is like q by 2a epsilon naught plus q by 2a epsilon naught, which is like q by epsilon naught a. Q by epsilon naught a is the net field produced at P. And that is only because of the charges on the 2 inner faces. That's only because of the charge on the 2 inner faces. The charges on the 2 outer faces are not participating in producing field at P. Clear? Now, what is Q? Q is the charge on this. So then, what is the surface charge density on this? Surface charge density on this is going to be Q by A. Right? So this could be looked upon as sigma by epsilon naught. The field produced is sigma by epsilon naught. Yes or no? Q by A replaced by sigma, the surface charge density, sigma minus sigma on this. The net field produced in between the 2 plates is going to be sigma by epsilon naught A. Right? So that's the electric field produced at P. The net electric field produced anywhere between the 2 plates is sigma by epsilon naught, is sigma by epsilon naught. Clear? Now, having said this, so the outer charges on the 2 outer surfaces in that context are passive. in the region in which it matters, they are not producing any electrical impact. They cancel the electrical impact of each other in between the two plates. Which means now charge here is plus sigma, charge here is minus sigma, right? And equal, I'm not, since these charges do not matter, I'm not designating and representing these charges anymore, no matter what the charge is, right? And the field here, E, like I said, is uniform in between the two plates and is of value sigma by epsilon naught. Sigma by epsilon naught, right? Now, this is the distance d. If this plate is at potential V1 and this plate is at potential V2, if this plate is at potential V1 and this plate is at potential V2, then, well, all points here would be at the same potential V1, all points here would be at the same potential V2. A conductor is going to be an equipotential entity, right? So, E results in the direction of the field a drop in potential, right? What's the drop in potential from this conductor to this conductor? E into D? E into D is the drop in potential, yes or no? So, drop in potential when you go from conductor 1 to conductor 2 is going to be E into D, is going to be E into D, which is like sigma by epsilon naught into D is the drop in potential, which is V1 minus V2, which is V1 minus V2. Yes or no? So that's a difference in potential. That's the difference in potential between the two conductors, which is, we will refer to as, say, V. V is the potential difference between the two conductors. Sigma by epsilon naught into D, right? Now, having said this, let me, once you understand this parallel plate thing, let me explain to you from a practical perspective how we define capacitance for such an arrangement, right? Such an arrangement has energy associated with it. There is an electric field between the two conductors, and there is energy associated in this electric field, which is the strain energy of this arrangement, Let me then go very specifically with this arrangement and explain a few things related to this, right? Can I wipe this off? Now, let me look at these parallel plates. Let me look at these parallel plates. And I connect a battery of EMF V. I connect a battery of EMF V. These are two uncharged plates. And I connect a battery of EMF V. Now, when I say EMF of the battery means between the terminals of the battery, the potential difference is V volts. This is the negative terminal of the battery, this is the positive terminal of the battery, and the potential difference between them is V volts. That means if I look upon this as 0 volts, then this would be V volts. That is what it means, Now let us see what happens when I do this. See, this is negative potential. This is negative potential. This potential is lower than this. This is 0 volts initially. This is 0, 0, right? So what happens is, there would be flow of positive charge from this to this terminal. Positive charge would flow from this terminal, this plate to this terminal. From this plate to this terminal, there would be flow of charge. Positive charge. When positive charge flows out of it, then it's left with negative charge because it was electrically neutral. And if it's now left with negative charge, its potential will decrease. Potential because of its own charge will decrease, right? As more and more positive charge flows out of it, the potential of this goes on decreasing. As more and more positive charge flows out of it towards the negative terminal of the battery, the potential of this goes on decreasing because it acquires more and more negative charge. When more and more positive charge flows out of it, more and more of negative charge would accumulate on it, and therefore this would become, the potential of this will decrease. Now, between these two, the interaction between the positive terminal of the battery and this. Now this is at a higher potential compared to this, right? So what this would do is, the positive charge that comes to this negative terminal from this plate, the positive charge that comes from the negative terminal to this plate would be supplied to this. The positive charge that comes from this plate to the negative terminal would flow past the battery, and would accumulate on this, thus raising the potential of this, yes or no? If more and more of positive charge accumulates here, the potential of this gets raised. You know what I'm saying? So then, what is going to transpire is, positive charge would be looped out of this, reducing the potential of this, would come to the negative terminal of the battery. The battery will do work to cause this positive charge to go from lower to higher potential. The battery would do work to elevate the potential energy of the charge, right? If it has to go from lower to higher potential, its potential energy increases. If the potential energy of the charge increases, there must be somebody who must be giving it that energy. There must be somebody who must be doing that work. The battery does that work. The battery loops this charge from this plate via the battery, and it accumulates on this plate. So more and more positive charge will accumulate here, while more and more charge would be lost by this. So this acquires more and more of negative charge, this acquires more and more of positive charge. The potential of this goes on decreasing, the potential of this goes on increasing, yes or no? After a while, the potential of this becomes equal to the potential of the negative terminal of the battery, and the potential of this becomes equal to the potential of the positive terminal of the battery. And once that happens, we say that steady state conditions have been achieved. We say steady state conditions have been achieved, right? You know what I'm saying? The potential of this becomes equal to the potential of the negative terminal of the battery. The potential of this becomes equal to the potential of the positive terminal of the battery, right? Once the potential of this becomes equal to the potential of the negative terminal of the battery, there would be no further charge exchange between this entity and the negative terminal. The potential of this becomes equal to the potential of this. There would be no further charge exchange between this terminal and this plate. And we then say that steady state conditions have been achieved. Steady state conditions have been achieved. You know what I'm saying, right? Now, when these steady state conditions have been achieved, the potential, this potential becomes equal to this potential becomes equal to this. That means the potential difference between these two terminals is also equal to the potential difference between the two parallel plates, right? So under steady state conditions, V becomes the potential difference between the two plates. Yes or no? This V was originally 0. both the plates. When we initiated this circuit, there was no potential difference between the two plates. These were uncharged plates and just a battery connected between the two plates. There was no potential difference. Eventually, V grows from 0 to V volts. V grows from 0 to V volts. Yes or no? Right? And while V is still changing, those conditions are referred to as transient conditions. While V still changes, those conditions are referred to as transient conditions. Right? Now, at an intermediate state, and eventually when V becomes equal to the EMF of the battery, or the battery rating becomes equal to the battery rating, that's when no further charge is looped from this plate to this plate. So what has the battery done? One, the battery only acts as a medium to transport charge from this plate to this plate. The battery never acts as a source of charge. The battery will never supply charge, as is commonly thought of. The battery will never supply charge. The only job of the battery is to loop charge from one entity to another. It will provide the energy. It will provide the energy to loop those charges from one plate to another, but will never act as a supplier of charge. The battery will only act as a conduit, a medium to transport charge, will never act as a source of or supplier of charge. Right? One. There is an intermediate state. In an intermediate state, there is Qi, which is being taken out of this supply and sourced through the battery, transported through the battery onto this plate. It accumulates on this. So one thing, whatever charge, the other important thing, whatever charge is transported by the battery from one plate to another, will accumulate only on the two inner faces. It will not bother about the outer surfaces, will accumulate it only on the two inner faces. And this is an intermediate state. Now, in this the EMF of the battery is V. In this intermediate state, the potential difference between the two plates is VI. And this is the final state. In the final state, a total amount of charge Q would have been lost by this plate, leaving this inner surface with minus Q, and would have accumulated on this face, on this inner surface plus Q. Whatever is lost by this is collected by this and is accumulated on the inner faces respectively. Right? This is the final state. This is the steady state. And this is an intermediate state. This state is also called the steady state. After this, no further charge would be looped from one plate to another. Now, no matter what, see, look at this intermediate state. What is the field between the plates in this intermediate state? Qi by epsilon naught A. Qi by A is the surface charge density. Sigma by epsilon naught is the field. Yes or no? In this intermediate state, sigma by epsilon naught is the field. Into D would be the potential difference between the two plates. In an intermediate state, yes or no? Vi is the potential difference between the two plates, which is electric field between the two plates, sigma by epsilon naught into D. That's the potential difference between the two plates in an intermediate state, while steady state is not yet achieved, right? And where what is Qi? Qi is the charge which is looped from one plate to another. What is Qi? Qi is the charge which is looped from one plate to another via the battery, right? And a potential difference Vi is achieved between the two plates in the process of this looping of charge from one plate to another via the battery mechanism, Then realize that this charge Qi looped through the battery, divided by the potential difference Vi produced between the plates. The charge looped through the battery divided by the resulting potential difference produced between the two plates Vi is what? Is epsilon naught A by D? Epsilon naught A by D? Yes or no? The greater the value of Qi, the greater would be the electric field between the two plates, the greater would be strain energy associated between the two plates, yes or no? The greater would be the potential energy of this arrangement. Yes, the electric field exists only between the two plates, right? So the greater the Qi, the greater the Vi, the greater the electric field between the two plates, yes or no? So strain energy increases as more and more of Qi accumulates, right? Eventually, this is the final steady state configuration attained. Now, no matter what, Qi by Vi, Qi is varying, Vi is varying, but Qi by Vi remains a constant, which is epsilon naught A by D. Qi by Vi, Qi looped through the battery divided by the potential difference produced between the plates because of Qi remains a constant, epsilon naught A by D. And what factors does it depend on? A and D are geometry factors, and epsilon naught is the medium factor, Yes or no? This then, for this kind of an arrangement, the electrical energy is a function of the charge Qi, the electrical energy between the strain energy between the two plates. And for this arrangement, we define capacitance as the charge loop between the two plates divided by the consequent potential difference produced between the two plates is defined as the capacitance of this pair of conductors. For this pair of conductors, the capacitance is defined as the charge loop between the two plates divided by the potential difference thus produced between the two plates Vi, which is epsilon naught A by D, and this is dependent on two factors, A and D, which are geometry factors, and epsilon naught, which is the medium factor. Yes or no? So the if there are two parallel plates, then the capacitance of the arrangement is defined as epsilon naught A by D. Yes or no? And if Vi is known to be the potential difference between the two plates at any given instant of time, then the charge on the positive plate is given by C times the potential difference between the two plates will give you the charge on the positive plate of the arrangement. Yes or no? Are you all certain about whatever I am saying? And how we have, in a certain sense, played around with our original definition to arrive at a more meaningful definition of capacitance if they were a pair of conductors. This is how we define capacitance of a pair of conductors. Then why do batteries stop working up? See, how it happens is, it's not because when you think it's discharged, this is not what it means. It is not discharged. What happens is, while the battery does work in transporting charge from lower to higher potential, it is doing work, right? When it does work, it does so by means of a, let's say in a chemical battery, by means of a chemical reaction. Now, those chemicals get depleted. Those chemicals keep getting used up and they get depleted. That's when we say it's discharged. But it's not discharged because batteries never supply charge. They only act as a conduit, a medium to transport charge. They will never supply charge. It is depletion of that chemical, for example, in a chemical cell, which leads you to believe that the battery is discharged. No, the battery is never a source of charge. It never gets discharged. It's the chemicals inside the battery which will get depleted and used up. Right? Now, having said this, so far so good. So this is the final state. Up to the final state, what is the charge that is looped through the battery Q. What is the potential difference produced? V. So this will also be Q by V. So charge in any intermediate state divided by the potential difference between the two plates in the intermediate state, or charge in the final state divided by the final potential difference between the two plates. They will always be the same and will be equal to the capacitance of this arrangement, which is epsilon naught A by D. Yes or no? Do you very clearly and transparently understand this? Huh? No issues, right? Now, if you allow me, I'll wipe it off, right? Now, see, so that's charging of the plates of a capacitor. A parallel plate capacitor is very commonly used in industry, and that's the mechanism of charging of plates of a capacitor. There is a transient state in which the potential difference varies, the charge keeps getting looped, and there is a steady state after which nothing perceptible occurs, right, electrically. Now, see, we had these parallel plates and uncharged plates, okay, and by means of a mechanism, it could be any mechanism, a battery mechanism or anything else, right, I loop charge from here and it accumulates here, and any looping will alter charge only on the inner surfaces, not on the outer surfaces. Like I said, the outer surfaces are passive towards production of an electric field between the plates of a capacitor. Now, from an uncharged to an intermediate state, see the capacitance of this arrangement is epsilon naught A by D, where what is A? A is the area of overlap of the two plates, the square root of which is much higher compared to the separation between the two plates, right? Square root of A much larger compared to D. This is a property of this arrangement, which will not vary based on which battery you're connecting or how much charge is accumulating, right? It's a fundamental property of this arrangement. Geometry and medium are the only two things that can impact this. So by some arrangement, I accumulate charge on this, let's say in an intermediate state, minus q prime and plus q prime. That means q prime has been looped out of this and has accumulated on this, right? This is an intermediate state, and eventually a final state, minus q and plus q, let's say. I'm charging it to eventually minus q plus q, the two plates of this arrangement. Clear? Now, let me attempt to compute the energy stored in the electric field between these two plates. Eventually, there is electric field between the two plates. Let me see the energy associated with the electric field, which is the strain energy of this arrangement. I seek to now compute the strain energy of this arrangement. Now, no matter what mechanism I have deployed to go from this state to this state, if this is the final state, irrespective of how this has been brought about or what mechanism brought about this, the energy associated with the electric field is going to be the same. Now, this is an intermediate state. Q prime varies from 0 to Q. Q prime varies from 0 to Q, final state Q. The potential difference between the two plates in this intermediate arrangement is V prime, which is Q prime by C. C is not going to change. Q prime by V prime will always remain C, where V prime is the potential difference between this plate and this plate, right? So V prime is going to be Q prime by C. C is epsilon naught A by D for this arrangement. The final is V, which is going to be Q by C, which is going to be Q by C. Clear? The final potential difference between the two plates is Q by C. Now, see, if I take an additional amount of charge dq prime from this, if I take an additional amount of charge dq prime from this and transport it to this, dq prime taken out of this and transported to this, the work done by an external agent, if I am not adding kinetic energy, will not depend on how I am transporting it. Path independent, it's a conservative field. So no matter what, if dq prime is transported from this plate to this plate, no matter how, its potential gets increased by an amount V prime. The charge that is being transported goes from lower to higher potential. That means it gets energized. It gets energized. And energized by what amount? It gets energized by an amount V prime into dq prime, yes or no? Work done by an external agent is going to be what? Charge into the potential difference to which it gets raised. Is the work done by the external agent, yes or no? Q into delta V, the increase in potential. So when I go from here to here, the potential of this charge dq prime increases by V prime. Yes or no? So what's the work done by an external agent? No matter what the external agent is. Or rather, don't think about the work done by an external agent. Let me correct this. Let me think about how much this charge dq prime gets energized. Let me think about how much this charge dq prime gets energized. So this dq prime gets energized by an amount V prime into dq prime. This is the amount by which this charge dq prime gets energized. Obviously, this energy has to come from an external agent. Some mechanism must provide for this energy, right? The total amount, the total increment in energy of the charges in going from this state to this state is going to be sum of all of this, where q prime runs from 0 to q, where q prime runs from 0 to q. That's the total increase in the energy of the charges, which is stored where? Which is stored as strain energy between the plates of this capacitor, which is stored as strain energy between the plates of the capacitor. This is the energy stored as strain energy between the plates of the capacitor. Now, this V prime, so this is the strain energy of this arrangement. V prime I can write as q prime by c, where q prime runs from 0 to q. Yes or no? When I integrate this, the strain energy then becomes q squared by 2c. Q squared by 2c, yes or no? That's the potential energy of this arrangement. That's the energy stored as strain energy of the electric field between the plates of the capacitor QC. If I integrate this, q prime dq prime is q prime squared by 2. When I supply the limits, then this is what I get. So this is the potential energy of the capacitor when charged to an amount q, when charged to an amount q. Q squared by 2c. Now, how does this get energy? What are the various ways in which this energy could get realized? See, if you connect this plate to this wire, then there is flow of charge from here to here. There is heat and light generated. Where does it come out of? It comes out of this q squared by 2c. Just to suggest that this energy could be realized, even though destructively it could be realized. Yes or no, it's available. Now it depends on how you want to utilize it, is another story. Just to be a prankster, you can just connect a conducting wire from here to here and you would find there is going to be heat, light, sound maybe in this wire, and you know there is energy that energy is actually an outcome of Q squared by 2C. Outcome of Q squared by 2C. So that's the energy. That's the electrical energy of this arrangement, Q squared by 2C. For a capacitor charged to Q coulombs on the two inner surfaces having capacity equal to C. Yes or no? Do you understand this idea perfectly or not? Now, this is the energy of the capacitor. Right? Now let's look at the mechanism that did this. For example, the battery. Let's look at the mechanism side of the story, the battery which did this, for example. Okay? I know what has eventually happened. The total amount of energy that is available for use is Q squared by 2C. But no mechanism is 100% efficient. No mechanism is 100% efficient. So to provide us with an energy Q squared by 2C, the amount of work that must have been done must have been more than Q squared by 2C. Yes or no? Of which only part, which is Q squared by 2C, gets available. Do you all understand this? Now, let me look at the battery side of the story. I have not yet looked at the battery side of the story. This was just a computation of how much of energy was available eventually when charged to Q coulombs on the two inner faces, Qn minus Q. Right? The battery side of the story, let me examine then. Clear? Now, see, eventually, and please understand these ideas. These are very important ideas and you can't ignore them. See, this was the battery, V volts. What did it do? It looped Q coulombs from here and posted them there, right? So this was eventually left with minus Q and this was left with plus Q. Let me look at the battery side of the story. How much energy was eventually available? Q squared by 2C was the energy which was at your disposal, which was, now this could also have been looked at. And what was the final potential difference between the two plates? So this Q was also C into V. Yes or no? Q by V was C, so Q is C into V. Q by V was C. So Q is C into V squared by 2C, which is half CV squared was the energy available as strain energy between the two plates. But let me see what the battery might have done in order to make this energy available. Let's see what the battery might have done to make this kind of energy half CV squared available. Now, Q, of course, the final charge Q is about C into V. Q by V is C. So Q is C into V, the final charge. Now, just the battery side. Even though the potential difference between the two plates of the parallel plate capacitor continuously varies from 0 to capital V, but the potential difference between the terminals of the cell, that is not going to change. That will remain V volts. Yes or no? That's not going to change. If this is 0 volts, this will be V volts. Now, the battery side of the story. Eventually, look at the battery. A total amount of Q coulombs must have flowed past the battery. A total amount Q coulombs must have flowed past the battery from 0 volts to V volts. That means this charge Q, in its attempt to flow past the battery, has got energized from lower potential to higher potential, means now it has more energy. More energy, and that energy must have come from the battery. That energy must have come from the battery. Okay, what did the battery do? From 0 to V volts, it energized this charge. So what is the work done by the battery? A charge Q, a total amount of charge Q, its potential is increased by an amount V. That's the work done by the battery. A total amount of charge Q, its potential is increased by an amount V volts. So the work done by the battery is, this is the extent to which these charges have got energized. Right? But what is Q? C into V. So which is CV squared. which is more than half CV squared. That means the work done by the battery is CV squared, of which only half is available. As we expected, right? No arrangement could have been 100% efficient. But the point is, agreed, it's not 100% efficient, but we need to investigate where this energy went. Of the CV squared that the battery supplied energy, only half CV squared was eventually available. That means half CV squared was lost. The battery seemed to be only 50% efficient. The battery seemed to be only 50% efficient. It provided CV squared but made only half CV squared available as strain energy between the plates of the capacitor. When charge was looped through this, you know, these were lead wires. They had some resistance, even though small or large, right? There was heat generated. There was a current through this. There was heat generated, right? So largely, the large part of halves, so the heat generated accounts for the maximum amount of energy which is lost. Heat generated, the Joule heating of the connecting wires. The Joule heating in the connecting wires accounts for large part. However, so there are three fronts on which energy gets dissipated in the process. This is the primary. The other two I will not discuss at length. They constitute a small portion. There are electromagnetic waves generated. We'll not bother about these right now. And then there is what is called self-inductance, for which also results in loss of energy. But so the total amount half CV squared which is lost gets delegated into these three fronts. It never happens. Zero resistance never happens. There will be resistance. No, then there will be resistance, a lead wire. So it will dissipate heat at a smaller rate, but it will dissipate through Joule heating only. You can't have zero resistance, right? So you cannot even account for it. So, however, when we talk of losses, we talk of losses primarily as heat generated or heat loss. Heat losses are these, right? So when we start with an uncharged capacitor and charge it to full capacity using a battery of V volts, then the battery is only 50% efficient. Doesn't mean that the battery will always be 50% efficient. See, if I have a charged capacitor and then I connect a battery to it, what happens? Let me examine that for you. And please understand the energy implications right now, right here in the class. Books might do a shoddy job in explaining this. It's a simple little thing, unnecessarily complicated. So please listen to me for the next 10 minutes with positive intent. Can I wipe this off?
Sir, here, if we use a good conducting wire, then also it will be half CV square.
Yes. I mean, it will vary only in the time it takes for that. The I square R rate at which Joule heating will vary. That's all. But the total amount of heat loss will still be the same, good or bad. The rate at which heat is going to be lost will be different. Now, I will just illustrate it with a few numbers. I'll just illustrate it with a few numbers, actual numbers. Say, there are two parallel plates and the capacitance of the arrangement does not depend on the charge. It's going to be always epsilon naught A by T. Suppose there is a capacitance, parallel plate capacitor of capacitance, say 1 microfarad. 1 microfarad is the capacitance of this arrangement. Okay? And say I give this 10 microcoulombs charge and I give this 6 microcoulombs charge. Okay. Let me first understand how the charges will get distributed on the four surfaces. On this, 10 plus 6 by 2, 8 microcoulombs. 8 microcoulombs. Yes or no? Q1 plus Q2 by 2, 8 microcoulombs, 8 microcoulombs. This would be 2 microcoulombs. This would be minus 2 microcoulombs. Yes or no? 2 microcoulombs minus 2 microcoulombs. This is the charge arrangement originally. Huh? There is electric field between the plates of the capacitor, and that electric field is caused by the charges on the outer surfaces or charges on the inner surfaces? Charges on the inner surfaces, right? So there is potential energy associated with this arrangement. How much is it? Qi squared by 2c. Qi is the charge on the inner surfaces divided by 2c. That's going to be the potential energy. So initial potential energy of this arrangement, which is strain energy, is Qi, which is 2 squared by 2 into c, which is 1, which is 2 microjoules, Qi squared by 2c. 2 microjoules is the initial potential energy of this capacitor, which is the strain energy in the electric field present between the two plates. You have a question, kya? Right? Now what I do is, I connect a battery like this. Say 1 volt battery like this. Now what would happen? There would be flow of charge till such time that the potential difference between the two plates becomes 1 volt, right? This will then be C into V. This would be minus C into V. So this eventually would be, see, since this is connected to the positive terminal of the battery, right? The charge here is going to be C, which is 1 into V, which is 1 volts, which is 1 microcoulomb, would be the charge here eventually. Yes or no? And the charge here is going to be minus 1 microcoulomb eventually. Yes or no? You know what I'm saying? The charge, when there is a, no matter what the initial charges were, eventually what is it that you're doing? Eventually, even if there was charge initially, this was 1 volts, please listen to me. This was 1 volts. 1 volt, right? The capacitance of this was 1 microfarad. So eventually, under steady state condition, there would be 1 volt of potential difference between them, right? This would then contain positive charge because it's connected to the positive terminal of the battery. This would contain negative charge because it's connected to the negative terminal of the battery. The charge here is going to be C into V. The charge here is going to be minus C into V plus Q and minus Q, final charge delegation on the two inner surfaces. So C into V, that means 1 into 1, that is 1 microcoulomb. 1 microcoulomb here. And this must be finally minus 1 microcoulomb. Yes or no? Isn't it? Now, this is the final charge distribution on the two inners. The battery will never touch charges on the two outer surfaces. Is important to remember. The battery will never touch charge on the two outer surfaces. The battery has to do only with charges on the inner surfaces. Why? Because it's only charge on the inner surfaces that are producing an electric field here, which in turn are producing a potential difference between the two plates, which in turn will eventually produce a 1 volt potential difference between the two plates. The charges on the outer surfaces are electrically, in a certain sense, they are not passive, electrically passive, right? The charges on the two outer surfaces are electrically passive. So the battery has nothing to do with charges on the two outer surfaces, right? Now, in order to go from here to here, what has happened? This inner surfaces was originally 2 microcoulombs. Now it is minus 1 microcoulombs. That means it has lost 3 microcoulombs. It has lost 3 microcoulombs, yes or no? Right? That means 3 microcoulombs must have flowed from here to there. 3 microcoulombs must have flowed from this plate to this plate, causing 2 to become minus 1. Now when 3 flows past this, that 3 added to minus 2 will make it 1 microcoulomb. Yes or no? That's the charge arrangement. Do you all understand this? 3 microcoulombs flowing from this plate to this plate, causing this to go from 2 to minus 1 and causing this, when 3 microcoulombs will come up here, then 3 plus minus 2 will make it 1 microcoulomb. Do you understand that? So this time, what is the charge that has flowed through the battery? 3 microcoulombs. What is the final arrangement produced? This is the final arrangement produced. Yes or no? Now, what is the final potential energy? The initial potential energy was 2 microjoules. What is the final potential energy? 1 squared by 2 into C, which is 0.5 microjoules. Is the final potential energy of this arrangement? Yes or no? Q squared by 2C. C is 1. Right? What is the work done by the battery? Can you tell me what is the work done by the battery? Yes. 3 microcoulombs flowing from lower to higher potential getting energized by an amount 1 volt. So 3 into 1, that is 3 microjoules must have been the work done by the battery. Work done by the battery is 3 microjoules. Q into the potential difference between the terminals of the battery. That's the extent to which this charge gets energized. That's the extent to which this charge gets energized. Now, see, this is what happens. What is it that we had? We had UI. To this UI, this was the total quantum of energy initially, right? The battery made its contribution. This is the work done by the battery. That was its energy contribution. Work done by the battery. Now, this was the total energy input. This was the total energy input to the final system. Where all did it get delegated? Part of it was available as UF, and the rest must have been losses. The rest must have been losses, primarily heat. Right? So what was UI? UI was 2 microjoules. What was the work done by the battery? 3 microjoules. UF was 0.5 microjoules. And losses could be now computed. The losses could now be computed. This time it's not 50% efficient. So then losses turn out to be 4.5 microjoules are the losses. These are the losses. 4.5, 5 minus 0.5, 4.5 microjoules are the losses produced in the process. Got me? Are you all okay with this? You want me to do that calculations? I can do that. The charges will flow the other way. Work done by the battery would be negative. You can see that. If you want, I can do fresh calculations by reversing polarity, or you can experiment on your own and then come up. I can do the same calculations with polarities reversed also. Try it on your own. So far so good, right? Does it make sense to all of you? Right? These basic ideas. So these losses, you know, even though I've told you there are 3 heads in which they get distributed: heat, electromagnetic waves, and self-inductance, but this is primarily heat. So sometimes we just call it heat losses. Even though there are 3 heads, but since it's mostly heat, we call it heat losses primarily, right? All's good so far. See, so this was parallel plate air capacitor, because the region, the medium between the 2 plates was air, so it was parallel plate air capacitor. Sometimes we talk of filling up this region with some other non-conducting medium, the region between the two plates, sometimes we fill up with a non-conducting medium which is not air, and it has permittivity other than 1. Permittivity other than 1. See, like I said, permittivity of the medium, divided by permittivity of vacuum or air, is relative permittivity of the medium, and is also referred to as K, the dielectric constant. This K is not 1 by 4 pi epsilon naught. This is dielectric constant of the medium. This is not 1 by 4 pi epsilon naught. This is dielectric constant of the medium. Which means the permittivity of the medium is going to be K times, this is epsilon naught. This is epsilon naught. So permittivity of the medium is K times epsilon naught. K is the dielectric constant of the medium. K is the dielectric constant of the medium. K is 1 for air. Now, so this is a medium with dielectric constant K. With dielectric constant K. Now, see, when there is charge plus sigma and minus sigma given to the two inner surfaces, plus sigma and minus sigma given to the two inner surfaces, this medium, originally has random dipoles. See, molecules, there is charge separation and they behave like dipoles. Etc. These are random dipoles. They have no alignment. When there was no charge, when they were exposed to no field, they were benign. They behave like random dipoles. The molecules of this dielectric medium, this is called a dielectric medium, and they behave like random dipoles. The net field that they produced was 0 because of the randomness. Because of the randomness of these molecules, the net field that they produced in this region was 0. However, when there is charge plus sigma and minus sigma given here, then this region is exposed to an electric field sigma by epsilon naught, right? When exposed to an electric field sigma by epsilon naught, these dipoles start to get aligned in the direction of the electric field. They now respond to the presence of this electric field. These dipoles now in the medium get aligned like this. They begin to get aligned like this. There is no more random. There is now an alignment, a definite alignment of the dipole, with the positive aspect of the dipole going in the direction of the electric field, the negative aspect of the dipole going opposite to the direction of the electric field. There is an alignment of dipoles that take place. Now, because of this alignment of dipole, realize that each dipole will produce an electric field in this direction, right? The electric field produced by the medium, this medium is going to be leftwards, which is going to oppose the C, yes or no? Which is going to oppose the C. That means the electric field in this region will now be less than E. E is when it was air, but now because of the medium, there is an electric field produced in this direction by this alignment of dipoles, which is going to mitigate or dilute E. So the electric field now in this region will be less than sigma by epsilon naught. The electric field here is going to be, the net electric field is going to be sigma by epsilon naught minus the electric field produced by the medium. That's going to be the net electric field here, right? the electric field will get diluted by a factor k. Sigma by epsilon naught was the electric field originally. Now instead of epsilon naught, you'll have k epsilon naught. K epsilon naught, isn't it? This is the medium factor. Wherever you see epsilon naught, now will become k epsilon naught, where k is the dielectric property of the medium, right? So the net electric field here, because of these two independent impacts, is going to be sigma by k epsilon naught, is going to be the net electric field produced in this region. K is the factor by which the electric field will get diluted, right? Now, see, essentially when these molecules get aligned, you know, the region between the two plates, these are the two plates, effectively, see, this was plus sigma and this was minus sigma. The region between the two plates now will be, this is the dielectric medium between the two plates, right? It's as if equivalently, you know, it's as if this surface, equivalently as if this surface has positive charge and this surface has negative charge on the dielectric slab, right? So it's as if there is a sigma I here and there is a minus sigma I there, which is said to be induced charge on the dielectric medium, So this plus sigma and minus sigma will produce sigma by epsilon naught there, whereas this sigma I and minus sigma I will produce sigma I by epsilon naught in this direction, which is the electric field produced by the medium, right? So then sigma by epsilon naught gets reduced by an amount sigma I by epsilon naught, where sigma I is the induced charge, and that must be the net electric field, which is sigma by k epsilon naught, where sigma I is the induced charge produced. Sigma I then, as you can see, the induced charge is sigma by epsilon naught into 1 minus 1 by k. Sigma by epsilon naught into 1 minus 1 by k, that's the induced charge produced on the dielectric slab, right? Remember, this k is not 1 by 4 naught, this k is a dielectric constant. So whenever it comes married with epsilon naught, you should realize that it's a property which is the dielectric constant, but not 1 by 4 pi epsilon naught. Unfortunately, we end up using the same symbolism, but remember, if it's coming married with epsilon naught, it's the dielectric constant and not 1 by 4 pi epsilon naught. Clear? And so which means now the capacitance of an arrangement, see, if there was an air capacitor, say everything remaining the same, this is D, the capacitance of this arrangement was epsilon naught A by D, right? Whereas if there was a capacitor with a dielectric slab between the two plates instead of air, and eventually there is plus sigma here and there is minus sigma, because this plus sigma and minus sigma is about the charge that is looped through the battery. The charge looped through the battery divided by the potential difference between these two will give me the capacitance of the arrangement, right? And if this was a dielectric slab of dielectric constant K, then the field here is going to be sigma by K epsilon naught. Right? And what is the potential difference between the two plates? Electric field into the separation D. This is D. The electric field, the net electric field has become sigma by K epsilon naught, yes or no? So the potential that drops from this plate to this plate is electric field, which is the net electric field after both the independent entities, is going to be this into this. right? This is like sigma into A divided by K times epsilon naught A into D. A is the area of overlap and sigma A is the total charge which must have been looped from one plate to another. Sigma A must have been the total charge looped from one plate to another, which would give me, now the capacitance of the arrangement is given by sigma into A divided by V, which is K times epsilon naught A by D, which is K times epsilon naught A by D. That means the capacitance is increased by a factor K. The air capacitor had epsilon naught A by D. With the dielectric slab filling this region, the capacitance becomes K times epsilon naught A by D. Very clearly, you know, when you place a dielectric slab here, the electric field here decreases. Gets right? Yes or no? So if the electric field decreases, now it has greater capacity to hold charge. So the capacitance of this arrangement must increase by a factor